non-trivial potential. Okay. So this example is that of linear harmonic oscillator. So we call this as oscillator, and of course we will talk about harmonic oscillator in one dimension. Okay. So this is non-trivial and
Sir, your
potential.
voice is very feeble. We can't hear properly.
I have increased the maximum of my sound. I think you have to increase sound in your device. Hello? Hello, is this better?
Sir, now it's
Yes, sir.
better.
Okay. Okay. So harmonic oscillator is a very important problem, and hence we try to do this in detail. So in general, there are many things that we can learn in terms of doing quantum mechanics of harmonic oscillator. So our starting point is the Hamiltonian of the system. The harmonic oscillator potential is given by a one-dimensional potential is given by half m omega square x square, where this m is the mass of the object which is oscillating, and this omega is basically called the natural frequency of the oscillator. And these are, once the oscillator is fixed, and these are constants of the oscillator. And you know, in classical problems you might have seen that a typical system is like a spring and block, and there is something called a force constant for the spring, and then the mass, this omega, is given by k by m. So this k is what is called force constant or a spring constant, whatever you call it. Okay, so this is the potential. Now this potential has a form like this. That is, if you are trying to plot v of x versus x, now this potential is something like this. So it's a parabola, okay, and it goes to infinity, and at x equal to 0 it is 0. Okay, so I'm sorry for the bad figure, but I am sure you understand what I'm trying to do. So there are two things that we can understand, we can notice immediately, that this v of x goes to infinity, the plus infinity, as x goes to plus r minus infinity. So this is first thing that we observe, because v of x is, as x goes to infinity, plus infinity or minus infinity, this goes to plus infinity. Now the second observation that I would like to make is that this v of x is invariant under this transformation x going to minus x. Okay, so that means this is an even function. So v of x is an even function. V of x is an even function. Now, we can certain conclusions can be drawn based on these observations. Okay. Now, the Hamiltonian is given by the kinetic energy, which is given by p square by 2m, plus the potential energy given by half m omega square x square. So this is our starting point. Our starting point is always the Hamiltonian. Okay. Now, what is our aim? Our aim in any problem in quantum mechanics is so our aim is to find psi of x such that h psi of x is equal to E psi of x. So what are the, so in general, you may have many such functions. So we do not know what is the nature of these energies and these functions. Are they discrete set or is a continuous set? All that we don't know right now, but we would like to solve this equation. That is h psi is equal to E psi. Now h, I have put a caret on h, which means that it is now it is now represented as a Hermitian operator. Now it is the time that we choose. At least I will try to do this problem in two different ways. So first is what I call it as a coordinate basis way. Sometimes this is called analytical method. So let us choose coordinate basis. So coordinate basis, which means now we will talk in terms of differential equations in x. Okay, so Schrodinger whatever this eigenvalue equation will now be recast as a differential equation, because in this coordinate basis x operator operating on some psi of x, any arbitrary, not necessarily, so some phi of x will be simply x multiplied by phi of x, and p operator operating on arbitrary phi of x will be equal to h bar divided by I into d psi d phi x by dx. So this is the operator correspondence with respect to coordinate basis, and we are going to choose coordinate basis, so we will use this operator correspondence. Now the eigenvalue equation can be now recast as a differential equation. So this implies, so h psi, h operator psi of x is equal to E psi of x can be written as minus h bar square by twice m d square psi by dx square plus half m omega square x square into psi is equal to E psi. So this is basically the eigenvalue equation, or what we call as time independent Schrodinger equation. Okay, so this is kinetic energy. So this is kinetic energy, this is potential energy, and this is E psi. Okay, so we have written down the Schrodinger equation. So our aim will be to solve this Schrodinger equation such that we find out what are the allowed solutions or allowed functions psi of x which satisfy this equation. Okay. Now to solve this one, let us try to do this in a few steps. So in the first step, let's try to simplify this equation Okay, so first step will be to recast the differential equation in terms of what are called dimensionless variables. This is sometimes we call this as non-dimensionalization of the equation. Okay, so variables. Now here there are two variables which have dimensions. Of course, others are also having dimensions, but the ones that we treat them as variables. One is x, which has the dimension of length, and the other is energy, because this energy we have not fixed. We want to know what are the allowed values of energy that will satisfy this equation, subjected to the boundary condition that is given. Okay, so now we ask a question that so what we will do is, let's try to um, first define a dimensionless length. Okay, so define some psi as x divided by L. We do not know what L is, but we assume that there exists some characteristic length which called L, such that I will always measure the length in units of L. Okay, so this is basically dimensionless coordinate. So xi is dimensionless and L is some kind of a characteristic length. And then you define your some epsilon as the energy divided by some E naught. E naught is also some characteristic energy. So this epsilon is dimensionless energy. Dimensionless energy. So the technique that I am going to show you now is a very general technique which is used for any differential equation. Okay, so please try to understand how we recast this in terms of this dimensionless variables. Now, of course, notice that this L and E naught have to be determined. They are not known yet. Have to be determined. So we have a freedom to determine them. Now what I will do, I will try to write down this equation in terms of these variables. For that, I will argue that d by dx is nothing but d by d psi into d psi by dx. And d psi by dx is basically 1 over L. So this is 1 over L into d by d psi. L is anyway a constant length. Then we have, so this equation can be recast as, so the differential equation. So maybe I will call this as equation 1. Okay, so the differential equation 1 can be written as, so I have minus h bar square by 2m into 1 by L square into d square psi by d psi square plus half m omega square L square psi square to psi is equal to epsilon into E naught into psi. And notice that here, when I write psi, psi is now a function of xi. Psi is now a function of xi. Now, let's try to, so we have to determine this L and E naught such that this equation can be written in a simple form. Okay, so for that what I will do is I will try to um, multiply this equation, multiply the equation with minus twice ml square divided by h bar square. So then what happens? This term will become simply d2 psi by d psi 2 minus, I have the 2 and 2 will get cancelled. So I have m square omega square L to the power 4 divided by h bar square into psi is equal to minus twice m L square by h bar square into E naught into epsilon psi. So this is what we have, this equation. Of course, there is xi square here. Xi square. Okay. Now I'm going to, this is an important trick. So I want you to observe this. So I'm going to determine, so determine, we have a freedom to determine L such that this coefficient is equal to 1. Okay, such that this coefficient is equal to 1. That means m square omega square L to the power 4 by h bar square is equal to 1. That means your L will be equal to square root of h bar by m omega. Okay, so this is called characteristic length of the oscillator. As you can see that it involves, besides the fundamental constant h cross, it involves angular frequency as the natural frequency and the mass of the oscillator. So this is once you know the characteristic length of the system, then length pertinent to this problem can always be measured in units of this, and that is what this dimensionless coordinate psi does. Okay. So the length is measured in units of L. Now we will try to determine E naught. Okay, so use the value of the L and determine E naught such that, so how do you determine E naught? You determine E naught such that this factor is equal to 1. Such that
Sir,
m is L square by h bar square into E naught.
sir, your voice is very low.
Hello?
Now better.
Yeah. So this implies I already know what is L. So I say twice m by h bar square into L square is h bar divided by m omega into E naught is equal to 1. So this implies your E naught, you can see this m cancels, h bar cancels. So you get E naught is equal to h bar omega by 2. Okay, so this is kind of a characteristic energy of the system. Okay, so this is characteristic energy of the oscillator. Okay, so if you, that means you are always trying to measure energy in terms of these units. Okay, so this is the situation. Then the differential equation with this identification of L and E naught, now the differential equation becomes, it comes to a very simple form, d square psi by d psi square plus epsilon minus psi square into psi is equal to 0. So this is the equation, whatever earlier equation that we have, equation number 1 is now recast into the dimensionless variables xi and epsilon. Xi and epsilon are dimensionless. Now I wanted to make, I wanted to tell you this is a very general procedure. Okay, so some remarks I wanted to make here. So remark 1 is that this method is general and can be used to any differential equation. Then the second comment that I wanted to make is that as you can notice, if you already know, otherwise you will see it, that E naught is equal to h cross omega by 2. Okay, and it is the ground state energy. Ground state energy of the oscillator. That means even for V of x, for which h psi is equal to E psi cannot be solved one can obtain the ground state energy by this procedure. That means the characteristic energy is always the ground state energy, and hence you can determine the ground state energy even though you are not able to solve this h psi is equal to E psi and get all the energy energy values, but I think at least one can attempt to get a ground state energy by this procedure. So that is why this procedure is somewhat more general than whatever we are doing here. So I wanted to make these remarks so that you can use it in other problems also. Okay, so after we recast this equation in this fashion, now we will go to the next step. Okay, so the next step is let us try to understand Of course, we have made those observations there. Okay, so let's try to understand what those observations mean. Okay, so x and xi are same because x and xi are simply related by a constant. So v of minus xi is equal to v of xi. This is what we have for that is, it's an even function. What does that mean? This implies psi of xi has to be either an even function or an odd function of xi. Okay, so it has to be having some definite parity. It can be even parity function or it can be odd parity function. Okay, so that is the consequence of this symmetry of the uh, potential. Secondly, v of xi goes to plus infinity as xi goes to plus or minus infinity. Okay, what does that mean? That means that, so this implies your psi of xi has to go to 0 as psi goes to plus or minus infinity. So this is basically the boundary condition on psi. The boundary condition. Okay, so the two observations that we made here, these two observations, they mean for the wave function the following thing. Okay, so boundary condition satisfied by the wave function, that wave function should go to 0 as xi goes to plus minus infinity, and the even function, the potential is even function, means that the wave function has to be of a particular parity. It can be even parity wave function or it can be an odd parity wave function. Okay, so these are the two important physical consequences of the nature of the potential on the wave function. Now, after we make this one, let's now try to get an asymptotic form of the wave function. Okay, so let's try to ask what is asymptotic form of psi of xi. Okay, so in the limit, in the region psi goes to plus or minus infinity. That means asymptotic means at a very large xi value. Okay, now let's go back to equation 2 and then look at the equation. Now, epsilon is some finite value. If xi is becoming very large, okay, so let us say, we will say that this psi of xi, as this xi go to plus or minus infinity, will go like psi tilde of xi. Let's call it like that. It will be a different function, so we'll call this as psi tilde of psi. Okay, and in equation 2, as xi go to plus or minus infinity, epsilon minus xi square can be simply written as minus xi square. Epsilon can be neglected because xi is so large now. Okay, so therefore the differential equation now will be d square psi tilde by d xi square is equal to psi square psi tilde. Okay, so that is the differential equation that one has to solve. Okay. Now it is possible to, by inspection, okay, by inspection, it is possible to say that suppose you have psi tilde of psi is equal to, let's say, e to the power plus or minus xi square by 2. Okay, suppose if you have a function like this, what will be your psi tilde prime of psi? Prime is d by d psi, okay? Psi tilde prime of psi. That will be equal to plus minus xi e to the power plus minus xi square by 2. Okay? Then what will be psi tilde double prime of psi? That means the second derivative. Second derivative will be xi square, okay, xi square and plus minus 1 into e to the power plus minus xi square by 2. Okay, but again, since xi square is very large, since xi square is very large, one can write this xi square plus minus 1 as xi square. So then that means this equation can be written as xi square into e to the power plus minus xi square by 2. So we note that e to the power plus xi square by 2 and e to the power minus xi square by 2 are solutions. Solutions, let's call this as equation 3. Solutions to differential equation 3. Okay, so the most general solution I would have to write. So my psi tilde of psi can be written as some c1 times e to the power xi square by 2 plus c2 times e to the power minus xi square by 2, where c1 and c2 are constants. Okay, so that is how I have to construct a general solution. Okay. Now I invoke one of the conditions that I have talked in the section 2, that is psi of xi should go to 0 as xi go to plus minus 1. Okay, just a minute. Okay, sorry. So this is so now, but the wave function has to go to 0 as I go to plus minus infinity. So that means since the boundary condition that psi tilde of psi should go to 0 as psi go to plus minus infinity, we require C1 to be equal to 0. Otherwise, that condition will not be satisfied. Thus, we have the asymptotic wave function psi tilde of psi will be equal to some constant, which I will call it as some C to minus psi square by 2. So this is the asymptotic form of the wave function. Now let us go back to our original. Okay, so now let's come to 4, where we are now going to say that the solution of differential equation 2 can be written as psi of xi is equal to, asymptotically it should go like this, but in the finite region we don't know how it goes like this. So let us call some arbitrary function f of psi into e to the minus psi square by 2. So this is dominant. Okay, so this is dominant as psi goes to plus minus infinity, and this of course we don't know what it is. This is dominant for finite value of psi. Okay, of course this has to be determined. Okay, so now how do we determine? We try to substitute in the equation 2. Okay, so let us first ask what is psi prime. Psi prime of psi is equal to f prime minus psi into f into e to the minus psi square by 2. So that is my f prime, psi prime. Then we ask what is psi double prime of psi. So that is equal to f double prime minus psi f prime. That is by differentiating this one. Now if I keep this and differentiate this one, I will get minus psi into f prime again. Okay, minus psi into f prime, and plus psi square into f. Okay, plus psi square into f, and of course there will be one more term called simply minus f into e to the minus psi square by 2. Okay, so that is, if I differentiate this one, I will get this term, and this term. Now if I keep this and differentiate this, I get minus xi into this. So that is, I will get this term, and then xi square into f, that is this term. So these two terms I will get. So these two terms are same, so I would have written it as minus 2 xi into f prime and so on. So let us substitute this. Substitute in differential equation 2. That is our original equation, this one. Okay. So then we have psi double prime, that is f double prime minus 2 xi into f prime plus xi square into f minus f. This is my second derivative term. Okay, into e to the minus xi square by 2 plus epsilon minus xi square into f into e to the minus xi square by 2. That is our psi is equal to 0. So you can see that this xi square f and this minus xi square f will cancel, and e to the minus xi square by 2 is a common factor which is not 0, and hence we will get a differential equation for f. So the differential equation satisfied by f is given by this d2f of psi by d psi 2 minus 2 psi into df of psi by d psi plus epsilon minus 1 into f of psi is equal to 0. So this is the differential equation that you will have to consider. By solving this differential equation, you will be able to find out what is the function f of psi. And if you know the function f of psi, then you can know the function psi of psi, because psi of psi is f of psi into e to the minus xi square by 2. Now notice that since psi of psi is equal to f of psi into e to the minus xi square by 2, and since e to the minus psi square by 2 is even function, it's an even function, we have to have f of psi to be either even or odd, either even or odd function. Odd function of psi. Okay. Now it is this kind of a differential equation one can solve using something called a power series method. Okay. Now the point is that since we know that this restriction is there, that it has to be some even function or an odd function, I can write down. So let me say that. So for example, if it is a polynomial, if it can be written in terms of a power series, and it is in powers of x. Now, if it has to be an even function, you should have only even powers of x. I mean xi. If it is an odd function, it should have only odd powers of xi. So we can write it in the following way. So let us say that. So let's say assume f of xi to be equal to f of xi to be equal to sum over some j is equal to 0 to infinity can say a to j into psi to the power 2j plus, let's have some s here, psi to j plus s. So essentially this is like some psi to the power s, and j is equal to 0 to infinity a to j into psi to the power 2j. Suppose, so depending on s, okay, depending on s, this will be either even function or an odd function. Because if s is, if you don't have psi to the s term, then this is an even function, right? So let's try to look at, so this is our solution. Okay, so this is our solution. Now let's try to substitute this in the differential equation. So let's call this differential equation as 4. Okay. So let us try to substitute this in 4. For that, let's write down what is f prime of psi. F prime of psi is equal to j is equal to 0 to infinity a to j into 2j plus s into psi to the power 2j plus s minus 1. And f double prime of psi is equal to sum over j is equal to 0 to infinity a to j 2j plus s into 2j plus s minus 1 into psi to the power 2j plus s minus 2. So substituting in equation 4, we get, so first is f double prime, so I will write that as j is equal to 0 to infinity a to j, oh sorry, yeah, that's fine, a to j uh, 2j plus s into 2j plus s minus 1 into psi to the power 2j plus s minus 2 minus 2 times sum over j is equal to 0 to infinity. Remember, I have 2 into psi here. Okay, there is a psi sitting here. Okay, so, and if I take that psi inside, then I will have a to j into 2j plus s psi to the power 2j plus s. And of course, our next term is epsilon minus 1 into sum over j is equal to 0 to infinity a to j. Of course, there is nothing here. Psi to the power 2j is equal to 0. Okay. Now, notice that notice that if we have yeah, so let us say that So from this term, okay, from this term, I will write the uh, first term separately. That is j equal to 0 term. So that is a0 into s minus 1. I will write that, and then that is given by xi to the power s minus 2 plus sum over j is equal to 1 to infinity. I have a to j into 2j plus s into 2j plus s minus 1 into xi to the power 2j plus s minus 2. Okay, so that is the first term, and then the remaining terms are same. Sum over j is equal to 0 to infinity aj 2j plus s into xi to the power 2j plus s.
Sorry, A2J, sir. Not AJ.
What? A to j epsilon minus j is equal to 0 to infinity a to j xi to the power 2j plus s is equal to. Now, in this thing that uh, since every power, every power of xi, I mean the coefficient of every power of xi should vanish. Okay, since the coefficient of every power of xi should vanish, and we should not have a naught to be equal to 0. If a naught is 0, then everything will be 0. Okay, so we want a naught to be not equal to 0. So that implies we get s into s minus 1 has to be equal to 0 from this coefficient. So for this coefficient has to be 0. A naught is non-zero, so s into s minus 1 has to be equal to 0. That means there are two solutions for s. S is equal to 0 or s is equal to 1. Now you go back and then inspect the way that we have written that remember, if s is equal to 0, s is equal to 0, your f of xi is equal to sum over j is equal to 0 to infinity a to j into psi to the power 2j. This is an even function. So even parity function or even parity solution. On the other hand, if psi s is equal to 1, if s is equal to 1, then your f of psi is going to be equal to xi into sum over j is equal to 0 to infinity. Okay, so the coefficients will in general be different. Okay, so but let me write down some other prime or something. Okay, no need to write prime. Some tilde into xi to the power 2j. So these are odd parity solutions. Okay, so depending on the value of s, you will have either even parity solutions or odd parity solutions. Okay, so uh, this is the situation. Now we ask a question that if you look at this particular term, that is, we have done some analysis on this, and then now you look at this particular situation. Now we can write this term. Okay, so let's try to write this particular term. Okay, so let's try to write this particular term as xi to the power 2 times j minus 1 plus s. Okay, 2 times j minus 1 plus s. Now, if I if I put if I put j minus 1 as some other index, okay, so what I'm trying to do is so consider this sum. Consider sum over j is equal to 1 to infinity a to j into 2j plus s into 2j plus s minus 1 into xi to the power 2j plus s minus 2. Okay, so what I'm going to do is I'm going to write this term as xi to the power 2j minus 1 plus s. Okay, and now set some other j prime to be j minus 1. Okay, this implies j is equal to 1 to infinity implies your j prime is equal to 0 to infinity. Okay, and j can be written as j prime plus 1. You follow? So now I can write this as sum over j prime is equal to 0 to infinity a 2 times j prime plus 1, okay, into 2j prime plus 2 plus s into 2j prime plus 1 plus s into xi to the power 2j prime plus s. Now j prime is dummy. Okay, so since j prime is dummy, the original equation, okay, so maybe I should call this equation 5. Okay, so the original equation can be written in the following fashion. So since j prime is dummy, we can call it j. There is no problem if you call it j. So then equation 5 we get, so we have a0 s into s minus 1 into xi to the power s minus 2 plus j is equal to 0 to infinity. So this term is, in all cases, this is what we have. And I have a 2j plus 2 into 2j plus s plus 2 into 2j plus s plus 1. Okay, so the coefficient is anyway xi to the power 2j plus s. So that is common in all terms, as you can see. Then I have minus 2 times 2j plus s minus 2 times 2j plus s into a to j. Okay, so that is from this particular term. And then I have epsilon minus 1 plus epsilon minus 1 a to j plus epsilon minus 1 a to j. This whole thing multiplied by xi to the power 2j plus s is equal to. So the general term, Okay, so the general term is going to be the following. That is a 2j, okay, I can write it as 2 times j plus 1 is equal to is equal to 2 times 2j plus s minus epsilon minus 1. Okay, so divided by 2j plus s plus 2 into 2j plus s plus 1. Okay, so this is what we call as a recursion relation. So now you understand why I said that if a0 is 0, everything is 0, because this is the recursion relation. Now this recursion relation will be, because s is sitting there, okay, since s is sitting there, if s is equal to 0, you will get even parity functions. If s is equal to 1, you get odd parity functions. So this is, okay, so this is something that we have. So you can notice that so this particular recursion relation is going to give you, suppose if I put j equal to 0, I have a0, then I have a2. So from a0 we get a2, a4, etc. Okay, or if you have from a1, then we get a3, a5. Okay, so that, so if j is equal to uh, if 2j is equal to 1, of course j is something that are okay, it is same, but then you have to simply multiply with, you put s equal to 1 here, and then correspondingly you multiply with a xi. Okay, so that is what it is. Okay, so this recurrence relation is fine. Okay, now you can, for example, let's say so let's try to look at s is equal to 0. Okay, then s equal to 0. So let's say that you s is equal to 0 and j is equal to 0. Okay, so then what happens? This recursion relation gives us a2 is equal to, so that is minus epsilon minus 1 divided by 2 into 1 into a0. Correct? Because j is 0, s is 0. So this factor is 0. Now, suppose if I take s is equal to 0 and j is equal to 1. Okay. So in that case, what happens? I will have 4 here. Okay. And j is equal to 2. Sorry, j is equal to 1. And this 2 into 2 is 4. So that is 4 minus epsilon minus 1 divided by, so j is equal to 1. So 2 plus 2 is 4 and 2 plus 1 is 3. So 4 into 3 into 8. Or in other words, I could have written this as 4 minus epsilon minus 1 into okay, I would write 1 minus epsilon divided by 4 into 3 into 2 into 1, and that is aj. Okay, and it goes like this. Okay, on the other hand, suppose if I take s is equal to 1 and j is equal to 0. Okay, s is equal to 1 and j is equal to 0, then I will have uh, so this equation will be simply a2 is equal to, I have to put s is equal to 1 here, so that means j is 0, so I have 2 times 2 minus epsilon minus 1, that is 2 minus epsilon minus 1 divided by s is equal to 1, so that means 3 into 2. Yes, so 3 into 2. So 3 into 2 into a0. Okay, but since I have xi multiplying this, because you look at our the way that we have written this here. So if s is equal to 1, there is a xi that is multiplying. Okay, so that this becomes 2j plus 1. Okay, so we can also write down this coefficients with a plus 1. So now a0 becomes a1. Okay, so a0 becomes a1. Now once that is there, then this becomes a3. So you get a1, a3, etc. If s is equal to 1. So this is how the solution is, uh, the power series is built up. Okay, now the question is that so suppose if we ask this question that so let us say that we have a so now let's look at okay, so this much I think is clear. Now let's ask what happens to this solution in the asymptotic limit. Okay, so that is let's call this as 5. So examine f of xi as xi goes to plus or minus infinity. As I goes to plus or minus infinity. For that, we will say, see, because j is running from 0 to infinity. Okay, so let us look at let's look at a 2j plus 1 divided by a 2j as j goes to infinity. Now look at this expression. Okay, so maybe we'll call this as equation 6. As j goes to infinity, this epsilon minus 1 can be neglected, s can be neglected, this becomes 4j. Okay, and here you have 2j and here you have 2j, this is 2j the whole square, correct? So 4j square. So as a result, what happens here is that this becomes 4j divided by 2j the whole square, which is basically that is equal to 1 by j. Okay, this is equal to 1 by j. Now you can see that a to j asymptotically, I mean as j becomes very large, it is going to be 1 by j. Now you can see that so in this asymptotic limit, now what happens is that your a to j plus 1 is like a to j divided by j. Okay, a0 is anyway constant, so let us look at j is equal to 1. So that means j is equal to 1. This means this is 2 a2, then this becomes a4, right? So a4 is equal to a2 divided by 2. Similarly, a6 is equal to a4 divided by 3, which is equal to a2 divided by 3 into 2. Okay, and so on. So in general, if you see, a to j becomes some kind of a2. A2 is some constant times a naught, so we can simply call this as a naught divided by a factorial. Okay, j factorial. So what does that mean? That means that if I go back and put this in the equation, that is let us say that our f of xi is equal to sum over j is equal to 0 to infinity a to j into psi to the power 2j. So which is equal to some a naught, some constant into j is equal to 0 to infinity psi to j by factorial j. Okay, so which I can write it as a naught into sum over j is equal to 0 to infinity psi square to the power j divided by j factorial, which is given by a naught into e to the power psi square. A naught into e to the power psi square. Now, if this is the asymptotic form, then this will be the function. If you retain all powers, all the infinite powers, this is going to be the function. But remember our solution. So recall, what is our psi of xi? Psi of xi is equal to e to the power minus xi square by 2 into f of xi. If f of xi is like this, that means it will go like e to the power plus xi square by 2, because this is plus xi square. Okay, and this does not satisfy the boundary condition. Okay, so this violates the boundary condition. And since this violates the boundary condition that psi of xi should go to 0 as xi goes to plus minus infinity. That means this f of xi should not dominate as psi goes to plus minus infinity. Okay, so what is the way out? The way out is that so this implies in f of xi we cannot afford to retain all terms in the power series. Up to infinity. Okay, we have to truncate the series. We have to truncate the series. This is the requirement. We have to truncate the series somewhere so that it is not dominating at infinity. Okay, so this requirement tells you that, okay, we go back to this recurrence relation. Okay, go back to this recurrence relation, and then we call this uh, so so let us say that uh, the truncation means the following. So the truncating the series, truncating the series implies for some j is equal to n, a 2n plus 1 is equal to 0. That means up to j equal to n terms are there, and after that it is 0. What does that mean? That implies so look at the numerator. So the numerator in the recursion relation in equation 6 must be 0. So what is the recursion relation here? So 2 times 2n plus s. S is of course, let's say 0. So then we have 2 times 2n. Okay, let me write down this s here, minus epsilon minus 1 is equal to 0. In other words, epsilon minus 1 is equal to 2 times 2n plus s, or epsilon is equal to 2 times 2n plus s plus 1. Okay, now so your n is something which is arbitrary. Okay, this tells you that this epsilon will take only these values for different values of n. So n is variable here. Of course, it has to be a positive integer, variable. It has to be a positive integer. But now you can see that suppose if I take s is equal to 0, okay, I take s is equal to 0, then epsilon is equal to s is 0, so I have 2 times 2n plus 1 as the value. But now let's go back. The energy is equal to E naught into epsilon. And E naught is 2 times 2n plus 1 into h cross omega by 2. So in other words, you can write this as, if I pull out 2, it is 2n plus half into h cross omega. Now it has to be and even n is equal to 1, 2, 3, 4, this n is equal to 0, 1, 2, 3, 4. This is 0, 1, 2, 3, 4, like that. This is give you only even numbers or even parity solutions. On the other hand, if you take s is equal to 1, then you have epsilon is equal to 2 times 2n plus 1 plus 1, which means your energy is equal to 2n plus 1 plus half into h cross omega. So in this case, n is again you can write 0, 1, 2, etc. Now it is easy to combine these two things because you see this is for even and this is for odd, and you can write simply this as En is equal to simply n plus half into h cross omega. Because if it is even, it is 2n. If it is odd, it is 2n plus 1. So it is simply basically n. So these are energy eigenvalues of the harmonic oscillator. And as you can see, your E0 is n is equal to 0, 1, 2, etc. So n is equal to 0 is the ground state eigenvalue. E0 is, even though I have used this same symbol earlier, so this is h cross omega. So note that the ground state energy is not 0. Okay, so note that the ground state energy is non-zero. Now this is called 0-point energy. Which is very important, and it makes a lot of interesting consequences. Now, to understand what this is, in general, if you have harmonic potential like this, classically, this is the lowest energy state. If you leave a marble, it will oscillate, and then finally it will rest. It will come to rest here. So this is the equilibrium position. So classically, x equal to 0, that means the energy is equal to 0, is basically the kinetic energy is 0, potential energy is also 0. That is the smallest energy state. Whereas quantum mechanically, there is some energy which is h cross omega by 2, and it cannot go below that. Okay, so this is called 0-point energy. So 0-point energy is a quantum feature. Okay, it is not observed in classical physics, and so one can ask a question: what is the origin of 0-point energy? Origin of 0-point energy. Okay, so think about it. I will.
So, uncertainty principle.
Yeah, that is true. But then you can try to get this energy starting from uncertainty principle. Okay, so this is as far as the energy is concerned, energy eigenvalues are concerned, and we can go back and then try to write down the wave function also in the same way. For example, let's say that you want to write down the ground state wave function. Okay, so for ground state, you know that means your n is equal to 0. It's an even parity wave function, even parity. Okay, so if you go back to this expression, a0 only will be there. Okay, so the ground state wave function will be psi 0 of psi is equal to a0 into e to the minus psi square by, and you have to get this a0 by normalization. Okay, so the normalization, that minus infinity to infinity a0 square and e to the minus psi square p xi is equal to, that implies you have a0 square into root pi is equal to 1, or a0 will be equal to 1 by pi the power 1 by. So this is basically 1 by pi to the power 1 by 4 into e to the minus psi square. And you can plot this function. This is the Gaussian, and if you plot psi versus psi 0 of psi, so it's a Gaussian centered at so this is a typical wave function. Okay, and if you can remember the potential is something like this. So the probability that the particle is there at the center, or the minimum of the potential, is high. And notice that if you give this much energy, okay, so classically, suppose let's say that this is the energy. So let's say this is the energy of the ground state. Okay, so these points, okay, so these points, so let's call this as minus x naught, and this as plus x naught. And classically, we know that these are turning points. So if you have energy given by this value, that means all the energy at x naught is the potential energy, then the particle will never cross this point. It will come up to minus x naught and turn back. It will come up to plus x naught and turn back. But quantum mechanically, since you see this wave function goes to 0 only at xi goes to infinity, okay. I'm sorry, I am trying to take this as x naught, but you could have simply called this as xi naught. That should be uniform. So let's call this as xi naught. But notice that in quantum mechanics, psi of xi modulus square is not 0 for xi greater than xi naught and xi less than minus xi naught. So that means it's not that it is particle will not go beyond these turning points. Particle will go beyond these turning points, and it's a nice exercise to find out given the wave function. Of course, I have given the wave function. Find the probability probability that the particle exists beyond the turning points for the ground state. Okay, the ground state wave function is given, so you can calculate from xi naught to xi naught to infinity and minus infinity to xi naught, and add those two probabilities, or calculate probabilities from xi naught to xi naught, and then subtract it from 1 minus that, whichever is easier. And how to find out xi naught? You know that energy for the ground state is h cross omega by 2. So this must be the total, this must be the potential energy at the end points. So that is half m omega square xi naught square. That should be the total energy. So this gives you xi naught square is equal to h cross by m omega. Correct. So basically, this is same characteristic length that we have talked about earlier. So xi naught is equal to plus minus, for ground state, it is plus minus square root of h bar by m. So you know this in terms of h cross, so you can try to find out what is the probability that the particle exists beyond the turning points for the ground. And the probability is not very small, it is rather appreciable. So this is another quantum feature. So 0-point energy is one quantum feature, and existence of the particle beyond the turning points is another quantum feature of the harmonic oscillator. And the first excited state is, of course, same thing, but you have to add, you have to multiply this with s is equal to 1. So the first excited state, state is given by psi 1 of xi. So that will be equal to some a1 xi into e to the minus xi square. Okay, xi into e to the minus xi square. And this a1 you can once again obtain by normalization, and it can be seen that by a proper rearrangement of these terms, it is possible to show I would recommend you to look at it from your previous semester's work on Hermite polynomials. It is possible to show that a general psi n of x will have some normalization constant, which I will call it as an, that depends on n, of course, into hn of xi into e to the minus xi square by 2, where this is called Hermite polynomial. Okay, now I wanted to make one remark here, namely, if you have noticed our previous discussion, I made a comment once that the polynomials, when you take a standard inner product, they will not be L2 functions. Okay, they will not be square integrable functions. So here we are going to define this inner product respect to a weight function called e to the minus xi square, so that the psi n of x, so some psi n star of x into psi m of x dx from minus infinity to infinity, this should be equal to delta n. Of course, some normalization constant. Okay, so I'm assuming that we have already made that normalization constant in this an, and this is equal to delta n. So these are orthonormal. Okay, so now if you ask a question that if I take integral minus infinity to infinity hn of x into hm of x dx, okay, hn of x and hm of x dx, and then when you, for arbitrary n and m, it is not, you cannot establish square integrability, but you have to assume that there is a weight function called e to the minus x square and dx. Then you can say that this will be equal to, of course, some normalization constant will be there here, and then delta n. Okay, so the inner product with a weight function has to be defined in order to make this kind of a, or you have to define the inner product in such a way that it will be finite. Okay, so this is the connection, and I would recommend you to look at your special functions, some discussion on Hermite polynomials, and then you will see at every time there are parallels between the differential equations that we have written down and your Hermite polynomial case, and you can see that the final power series that we have written, different books will try to write this power series in different ways, but then that is not important. The important thing is that we understand what we have done. So please look at that, and this is essentially the method called analytical method or power series solution method to solve Schrodinger equation for harmonic oscillator. Okay, if there are questions, you can ask.